Alright, so the first video talked about forces that were applied to an object that was just sitting on a flat surface, except the forces were being applied at an angle. Now we're going to have the surface at an angle. So let's start out just drawing a normal free body diagram of an object just sitting on a flat surface. So I'm going to have, again, my XY plane. And let's have an object sitting on a flat surface that is parallel with my x-axis. Okay, so I know forces acting on this. I'm going to have my normal force that will act in that upward direction in the y direction. I know I'm going to have my gravitational force, which is going to act downward in that same y direction. I'm going to have my force, maybe a force applied pushing along the x-axis, and maybe a force of friction pushing along in the negative x direction as well. So those would be some forces that could be acting on here. Now, think about what would happen then if I tilted this. So it's now on an inclined plane. I'm going to draw a little inclined plane here so that we can see it. And say, all right, it's being inclined at some angle theta, maybe 20 degrees, maybe 30 degrees, whatever. Now, let's think about the forces that are acting on this thing. Well, the first force that you guys are always awesome about telling me is the force due to gravity. And so here's my force due to gravity. We know that that is always going to act straight down, right? Okay, take a look what just happened. This is no longer acting in the y direction. Now, my force of gravity is actually acting at an angle to my negative y-axis here. And so what I'm going to have to do is I'm going to have to split this up into the x and y components. There we go. Because we still need to deal with normal force, and we still need to deal with the forces that are going to be acting along my x-axis. And so if I want to find the sum of the forces acting on all of my on my object here, I'm still going to have to deal with finding the forces acting in the y direction and the forces acting in the x direction separately. You might be wondering, well, why don't we just, let's say, you go over here for a second. What if we drew it like this? And this is y, and this is x, and here's my little box sitting on the, oh, wait, that doesn't look right at all, does it? I was trying to do something cool. And then I screwed up. It's okay. Erase, erase. I want my object clearly to be sitting on the inclined plane and not the x-axis. Duh. Okay, here we go. Okay, so then if my object is sitting on the inclined plane, there it is, well then we know that its weight is still going to act straight down. Okay, so now I can say that the force of gravity is acting straight down. However, if I have a person who's going to be applying a force, let's say a person is going to push this box up the hill, like that. Well, now I have this force that's acting at an angle. And then, of course, if I've got an object, it's sliding against the inclined plane, well, then I'm going to have some force of friction acting also at an angle. And then I'm going to have to deal with my normal force, which we know that normal force always has to be perpendicular to the plane. It has to make, if I drew it all the way down, it would have to make a right angle with the surface. And so now I've got this force that's also at an angle. And now we've got only one force that's not acting at an angle to the x and y. If I draw my x and y tilted so that my x-axis is parallel with the surface that my object is sitting on, then if I draw my normal force that is in the y-axis, if I have some force being applied to the object to push it up the incline, force applied, well, that's in line with the x-axis, and then my force of friction would then also be in line with my x-axis. And now the only vector that I have to split up into its x and y components is my force due to gravity right here. So instead of splitting up 1, 2, 3 vectors, I'm only splitting up one. So which one's easier? I think this one is, personally. Hopefully you agree. If you don't, then maybe you're a glutton for punishment. I don't know. So here's G. And so one thing that's really important to know about this diagram that I want to make sure that I tell you before I run out of time here is that if I have an object sitting on this inclined plane and it's not accelerating in this y-axis, it's not accelerating this way or that way, which it really shouldn't be. We don't want it to be flying around. It should be at rest on this y-axis. We don't want it to go up and down. Otherwise, it would be either flying off or the plane would break. That would tell me that this force here has to be equal and opposite to this force down here. So what that is telling me is that my normal force is equal in magnitude and opposite in direction to my force due to gravity that's acting in the y direction, which is this piece right here. So this vector and this vector have to be equal in magnitude and size and opposite in direction. We also know that if we're applying a force up the ramp, well, we know that gravity is applying some force down the ramp. That's this force vector here. So we would have to figure out this force vector to figure out the sum of the forces that are acting on this object in the x direction, so that we can figure out how hard do you have to push to get this object to go up the hill. And so that would be another thing that you could do. And so let's talk about how we would actually calculate, how we break this up. One thing that we need to know is that this angle right here in this triangle that I've created, this blue triangle, is actually also equal to theta. That same theta right over here. And that is a trig property based on these triangles. And if you can show me a proof that these two angles are congruent, I will give you extra credit. I need to see that proof before Thanksgiving break. Okay, so if you can prove that these two angles are congruent, and they are, then I will give you extra credit. I need to see that before Thanksgiving break, though. The offer is null and void after Thanksgiving break. Okay, real quickly before I run out of time, if this is theta then this is my opposite side, and then y is my adjacent side. So typically we associate y with being sine and x as being cosine, but it's flip-flopped here. Here, x is going to be sine and y is going to be cosine. So sine of theta is going to be equal to opposite, which is x, over hypotenuse, which is Fg, the actual weight of my object. And then cosine of theta is going to be equal to my adjacent, which is y, divided by Fg, which is the weight of my object. So that's how you would break those up into their pieces. And then when you come to class, we are going to do some practice problems with it. Thanks for watching, and I'll see you in the morning. Bye.